Good afternoon. My name is Olivier Chiello, and I work at the Joint Research Unit in Environmental Acoustics, a joint laboratory of the New Gustave Eiffel University, and the French Center of Expertise, CEREMA. I'm going to present to you the work carried out for the most part by Annabelle Caura during her master's internship in our laboratory under the supervision of Marie-Agnès Pallas and myself. As you certainly know, the new Gnosos prediction methods must now be used by all member states to carry out noise mapping within the framework of the European Noise Directive. The performance of the methods is highly dependent on the relevance of the input data used, and some difficulties may arise when the new Gnosos models are very different from the previously used models. This is the case in France for rare emission models, which are much more detailed in the Gnosos method. The case of heavy rail is not critical because national operators have a sufficient number of models and experimental data. This includes notably the default data proposed in the annex of the Gnosos method. This is not the case for light rail, especially trams, for which few data exist, despite the large variety of tracks in vehicles. The aim of this work is to propose and test a simple method to adjust Gnosos input data for tramways based on available pass-by measurement of commercial service vehicles. This first test was carried out on the Lyon tramway network in France. I will begin my presentation by reminding you of the principles of the Gnosos emission model for rail. I will also talk about the available measurements which are used in this test to identify the Gnosos input data. I will then detail the proposed identification methods, namely the emission and propagation models used to calculate the pass-by indicators, and the inverse method itself. Finally, I will present the results obtained and the main conclusion. The first characteristic of the Gnosos emission model is its multi-source aspect. Rolling noise, traction noise, and aerodynamic noise are differentiated. Traction noise and aerodynamic noise are characterized by sound power spectra with explicit speed variation constant for traction noise and proportional to the speed logarithm for aerodynamic noise. Rolling noise is taken into account in more detail, as we'll see later. The sound powers are then distributed over a homogeneous traffic section at two predefined heights of 0.5 and 4 meters, the distribution depending on the type of the source. The sources also have predefined directivities, and other type of noise can be taken into account in certain situations, such as bridge noise, impact noise, and squeal noise. Rolling noise is taken into account in a more physical way, as shown at this diagram. A distinction is made between the excitation parameters, namely the wheel and rail roughness spectra as a function of wavelength, and the parameters representing the vibroacoustic efficiency of the structures, namely the vehicle and track transfer functions. These four main input data are necessary to calculate the total power of the rolling noise. It should also be noted that the variation in speed obtained is implicit and is related to the conversion of the wheel-rail roughness spectra, expressed in wavelengths, into frequency spectra. The acoustic measurements used for our identification were carried out 2 years ago by the association Acoustic, which is in charge of producing noise maps for Greater Lyon. Pass-by sound levels were measured in accordance with ISO standard on 4 track sections, using 2 microphones placed at 2 different heights. As you can see, the 4 tracks are quite different, whether in terms of rails, supports, or coverings. The measurements were performed on 2 different types of tramway running at various speeds for a total of about 60 pass-bys. In addition to the acoustic measurements, we were also able to measure rail roughness on the 4 track section tested, as well as wheel roughness on a small sample of rolling stock. Only the results of corresponding to one type of tramway are presented today, which represents about 20 pass-bys. The model used for the identification includes an emission part incorporating the Knossos methods for the calculation of the sound powers corresponding to the rolling noise and the traction noise. The directivities and the heights of the sources predefined in Knossos are used. We have also added some information about the longitudinal position of the sources on the train set. The propagation part consists in calculating the different attenuations in order to determine the sound pressure level at the receiving point. The pass-by sound level is then determined by summing the contribution of the sources and integrating over the tram during pass-by. An inversion of the model is finally performed to identify the unknown parameters from available measurements. In this first stage, vehicle track separation is not intended, and one overall transfer function is to be identified. It should also be pointed out that the whole method is carried out in frequency bands so that the two input parameters are spectral. So the emission model consists of a set of point sources placed on the train sets as follows. For traction noise, upper sources are uniformly distributed along the train set and lower sources are placed on the motorized bogies. For rolling noise, only lower sources are placed at the wheel sets. The total sound power level in red, corresponding to the traction noise, is equally distributed between the upper and lower sources and between each source at the same height. The sound power level of each rolling noise source is calculated from the overall transfer function in red and the effective combined wheel ray roughness level, which is determined from the measured roughness level and the contact filter in accordance with the Knossos method. The two parameters in red are to be identified. The propagation model first consists in calculating for each source and for each position of the train set the sound pressure level at the receiving point from the sound power level of the source, its directivity, and an attenuation term. This term includes the attenuation due to geometrical divergence, the attenuation due to atmospheric absorption, and the attenuation due to ground effect. The first two terms are calculated according to the Knossos method, but the attenuation due to the ground effect is calculated more precisely from the spherical reflection coefficient and the ground impedance. The choice is linked to the fact that we are interested in receiving points relatively close to the sources with homogeneous ground. The last step consists in summing the contribution of the sources and integrating over the position of the train set during pass-by. The pass-by sound level can then be expressed explicitly as a function of the two parameters to be identified. For one pass-by and one microphone, the previous relationship can be written as a linear relationship between the equivalent quadratic pressure and the two unknown variables. If we combine the results from n different pass-bys obtained on the two microphones for one given track section, we obtain a linear system with two n equations and two unknowns. The results obtained for the four track sections can also be grouped together. The transfer function has to be identified for each section due to the track differences, but the sound power corresponding to the traction noise is independent of the track. We thus obtain a system with 40 equations and 5 unknowns. This system is inversed using the least squares optimization methods, adding some constraint of the unknowns to avoid getting non-physical results. Estimates of the emission parameters obtained with this method are given in these figures. They are compared with some default values provided in the Knossos method. On the left, you can see in blue the estimated power spectrum corresponding to the traction noise. The result is quite realistic and compares well with reference spectra in terms of order of magnitude. The spectrum is rather discontinuous with some maxima in certain frequency bands. Outside of these peaks, levels drop sharply to the limits imposed by the identification. It seems that the contribution of traction noise is too small compared to rolling noise to be precisely identified. On the right, you can see the estimated transfer function. The spectra obtained for site B and C in red and yellow are quite close to the default Knossos data, but always several dB lower, which is not surprising for the tram. For both sides, the transfer functions need to be well identified, considering that the estimated rolling noise is always above the traction noise, as we will see later. On the other hand, the results obtained for site A in blue are questionable because all the pass-bys are at low speed. So rolling noise is low and traction noise is the main contribution to the total noise. This leads to some difficulties in estimating a consistent transfer function for these sites due to the various uncertainties. Conclusions are similar for site D at low frequencies, for which the low values obtained are probably not very accurate due to the predominance of the traction noise. The figure on the right compares the global pass-by sound levels obtained from the estimated parameters in purple with the major levels in yellow. The results are given for each size as a function of speed. The contributions of traction noise and rolling noise are also given for the model. You can note the predominance of traction noise for site A, which is related to low speeds. For this side, it should also be noted that the pressure level of the traction noise is higher than in the other sites due to the concrete pavement. On the other sides, the rolling noise is rather predominant, with speed variation slopes between 22 and 29, which seems correct in view of the results of the literature. The gaps between measured and calculated results can be more easily visualized in the figure on the left. It can be seen that these deviations are within plus or minus 2 dBA. Let me now conclude. The aim of this work was to empirically determine the Knossos emission parameters of some trams of the Lyon network. The parameters sought are the power spectrum related to traction noise and the overall transfer function relating to rolling noise. These parameters are determined on the basis of a few measurements carried out on site, pass-by noise levels according to ISO standard, and wear roughness according to European standard. A global identification process is proposed by combining results from sites with different tracks, pass-by at various speeds, and 2 microphones. Results are satisfactory for a first study with acceptable global errors. Difficulties may arise in separating sources when the speed range is not sufficiently large. Further work is in progress in order to increase the performance of the inverse method. Results of some vibroacoustic models of tram tracks, combined with track decurate measurements on site, will also be used in order to separate the track and vehicle contribution to rolling noise in the transfer function. Thanks for your attention.